always happy when it's Julia's turn comes around to give the talk. Julia is a professor here, and as I hope you all know, and will be anything else about her. I want to hear what she will talk to us about in bipartite matching. Thank you.
Thanks, Nate. Tell me if it's too loud, okay?
You're good.
Sounds good. So this talk is about fast combinatorial algorithms for bipartite matching, and this is joint work with Chuzhoy. So probably many of you know what is the bipartite matching problem. So you're just given a bipartite graph, and you want to find a matching in this graph of largest cardinality. Matching is a bunch of edges that don't share any endpoints. So here you can see matching of size 3. And as you have probably seen in algorithms classes, you can cast this problem as a special case of max flow. So how you do it, you direct all edges from left to right. You add a source that connects to everybody on the right, on the left. You add a destination to which everybody on the right is connected. You set capacity of every edge to be 1. It's an instance of max flow, and it's in fact equivalent to a matching problem. Why? Because if you take any matching, you can just extend it to a flow of the same value. So here the red edges carry 1 flow unit and blue edges carry 0 flow unit. And the other direction is also true. Whenever you get integral flow, so every edge carries 0, 1 flow units, you get the matching because you just take these edges in the middle that are red into your matching and you're done. Okay, so obviously if you have an algorithm for maximum flow, you can solve bipartite matching. This is like very well known. It's taught usually in algorithms class and so on. And interestingly, what people are less aware of is that the other direction is also true. If you have an algorithm for bipartite matching, you can actually use it to solve maximum ST flow if all vertex capacities are unit. So it's really cool. So in some sense, bipartite matching and flow are the same as long as unit vertex capacities. Yeah, I know it's surprising. Okay, so going back to this problem. So I said, okay, we can think of this as a max flow problem. And so as such, I can apply any of the max flow algorithms to it. For example, Ford-Fulkerson. And this is, again, algorithm most of us have seen in class. And in our context, I'm just going to start with an empty matching, and then I'm going to grow it iteration by iteration. So how? So when we start an iteration, we're given some matching, and we said, well, this matching defines this flow, right? And again, red edges carry 1 flow unit, blue edges carry 0 flow units. And next, we compute a residual flow network. But in this case, all capacities are 1, and all flows are 0 and 1. So residual flow network is very simple. You just reverse the directions of all red edges, and you're done. This is the residual flow network. Okay, next, we compute any ST paths in this residual flow network. For example, this one that is shown in fat edges, and sometimes we call it augmenting path, because next what we're going to do, we'll augment the flow and the matching along this path. How? I'm just taking these edges that are on this path in the middle, and I flip them. The red ones become blue, the blue ones become red. And it doesn't work so. And this way, wait. What happened? And this way we get a new matching, and now its cardinality is 3. And we keep on going like this all the way to the optimal solution. And if you sort of remember from your algorithms class, you can implement this algorithm to run in time m times n. Why? Because there could be as many as n iterations. Every iteration takes time of m, so of m times n. And this is an algorithm of Ford and Fulkerson from 1956. In 1973, it was noticed by Hopcroft and Karp that you can do it faster. And once the idea is that instead of improving 1 by 1, little by little, you do it in bulk. So what you do, you go to the residual flow network, and now you want to compute a maximal collection of shortest disjoint paths. And these paths are disjoint, so you can augment your flow simultaneously on all of these paths, and you're done for 1 iteration, right? And they show that you can get m squared n running time using this idea. And this is it. This is where we stood for a very, very long time. And now it was noticed that if you use fast matrix multiplication, you can also use it to solve this problem. You get a little bit faster time if your graph is sufficiently dense. If the graph is not very dense, this is still the best. So I'm going to list these under combinatorial algorithms, even though some people don't count matrix multiplication. I mean, matrix multiplication is not combinatorial, strictly speaking, but let's be generous. So this is where things stood for a very, very long time. And in the meanwhile, a new paradigm emerged that completely revolutionized this whole field. And the paradigm is the use of continuous techniques in order to solve flows and other problems. So the idea is pretty simple. You just cast your flow problem as linear program, then you apply interior point methods, and you try to speed things up there. And this led to a burst of activity. There is, I'm sure, I'm not listing all of the papers, there is a long list of papers. Several of them are big breakthroughs, and they were getting faster and faster algorithms for max flow, for bipartite matching, for related problems. And this culminated like literally a year ago, where using these techniques, an almost linear time algorithm was achieved for maximum ST flow, bipartite matching, min cost flow, all of these problems. So what is common to all these results, again, is that all of them are based on continuous techniques, specifically casting your problem as LP, and then using interior point methods to solve this LP. So to summarize, here's where things stand. If you're using these continuous methods, you get super fast algorithms. But if you stick to old-fashioned combinatorial algorithms, then 1973 result of Hopperov and Karp is still the best that we have. And so a natural question to ask is this situation necessary? Do we need to use continuous methods to get fast algorithms? And can we get faster algorithms by using combinatorial methods? Now, I'm very fully aware that it's not well defined what are combinatorial methods. We sort of intuitively know what they are. And also you may ask, why do we care, right? We have this really fast algorithm. Why do we want to do something different? So let me tell you a little bit motivation for that. So first of all, combinatorial techniques, they tend to be more transparent. They actually show us how we build the flow, and they teach us things. As an example, we know that max flow can be solved through linear programming, right? When we teach max flow in algorithms classes, we don't say, oh, it's a linear program, just feed it to LP solver. We show for Falkerson, we show other algorithms. Why? Because this teaches us about structure of the graph. This teaches us some notions such as residual flow network, augmenting paths, and so on. And these are very important. They're useful in all kinds of places. And second, these are really basic problems. So we hope to develop some tools and techniques that can be used in some places where continuous techniques cannot be used. And here, a motivating example is maximum matching in general graphs. So this seems to be a much more difficult problem. And there is LP relaxation for it, but it has exponential size. We simply don't know how to use continuous techniques for this problem. It's not like there is some natural pathway for this. All algorithms are using combinatorial methods that are using augmenting paths technique. So if we want to get faster algorithm for this really important problem, we should first design faster algorithms that use these techniques for bipartite matching. And third motivation is that, again, both matching and flows, they're such basic problems, they have to be used everywhere. They're just building blocks from which we build our algorithms. And this includes classical setting, but also online algorithms, distributed algorithms, dynamic algorithms, and so on. And in some of these settings, the continuous techniques are simply difficult to apply, while combinatorial methods, they can be just plugged in very naturally. So with this motivation in mind, we go back to this question, can we get faster algorithms for maximum matching that only use combinatorial techniques? And in this talk, we'll see that the answer is yes. And the answer is based on two papers. The first paper, both of them are joint work with Intercana. So the first paper just appeared in SODA. This is the running time that it gets. So it already beats Hopperov Karp and matrix multiplication if your graph is moderately dense. And the second one is about to appear in stock, and this one gets close to n² running time. So if your graph is dense, this is pretty much the best you can hope for. If your graph is sparse, there is still room for improvement. And as I said, this immediately automatically gives algorithm for max flow with unit vertex capacities with the same running time. So, you want to ask?
Yes, I'm just comparing in my head. It's okay.
Okay. So most of the talk today, I'm going to talk about this result because it's like really surprisingly simple and easy. It's just a couple of observations and then a little tweaking of existing algorithms. The second one, I'll maybe say a few words about it at the end. It's much more technical, and most of the time I'll be talking about this one. Okay, so first of all, we do a very high-level view of the algorithm, and it's sort of standard stuff. We just start with an empty matching, and then we're going to grow it over the course of polylog n iterations. And we keep on growing it until it becomes quite large, not all the way to optimal, but close to optimal. And at this point, we're going to switch to Ford-Fulkerson because just a few iterations are left to augment it, and this is how we get all the way. We'll see in a minute why exactly we'll switch between the two algorithms. So to make this work, there is this main subroutine. So what does the subroutine do? It is given the current matching, and it wants to get a bigger matching. So throughout, I'm going to denote by delta the difference between the optimal matching and the current matching. So what we want to do, we want to get a matching that is much bigger. So the cardinality is the original one plus delta over polylog n. If we got delta here, we will get all the way to optimal. We don't ask that much, we stop a little bit before. And the running time is going to be this. Now, if you look at the subroutine, obviously there's going to be at most polylog n iterations. And also, as long as delta is large, the running time is pretty good. When delta starts getting small, the running time is not so good, but this is when we're pretty close to the optimal solution, so we can just switch to Ford-Fulkerson, run delta more iterations, and we're done. And by just carefully balancing where exactly we switch from one algorithm to another, this is the running time that we get, and this is this other result. Okay, so now we're going to look at this main subroutine in a little bit more detail. So we start with some matching M. This is the current matching. And as we said, well, it defines flow in the flow network, like this, right? Again, every red edge carries 1 flow unit, blue edges carry 0 flow units. As before, we compute the residual flow network. Again, this is just reversing the red edges like this. And one thing that is true in any residual flow network, it always contains a flow whose value is optimal flow minus the value of the current flow. This is just a property of residual flow networks, that's always true. In our case, what this means is that there is a collection of disjoint ST paths whose cardinality is delta. Delta, which is opt minus the current matching. So what we ask from the subroutine to do is not to recover all of these paths, but recover a large number of disjoint ST paths, how many delta over polylog n. And then once we do it, we augment the matching through these paths. In other words, if you look at this, at what we want to do here, what we want to do is solve approximate max flow in the residual flow network. Okay? So basically what this is saying, in directed graphs, if you can solve flow approximately, you can solve it exactly. This is like well-known stuff. And the main question is how to do this efficiently. So this is just a summary of what we want from now on. We just want a fast algorithm that computes a lot of disjoint ST paths, knowing that delta such ST paths exist. So now I want to tell you a little bit about the structure of this residual flow network, just a few small observations. So let's delete S and T from here. What do we get? Well, we get back the bipartite graph, right? So these red edges, they correspond to matchings, to the edges of the matching, and they're directed from right to left. So every vertex is going to be incident to at most one right to left edge. So we're going to talk a lot about graphs like that, so I'm just going to give them a name. I'm going to call them well-structured graphs. So generally, a well-structured graph is a directed graph that's bipartite, so edges go in both directions. And if you look at the edges that go from right to left, then every vertex is incident to at most one of them. So these red edges, I'm going to call them special edges because they have this extra property, and blue edges are going to be called regular edges. And as I said, we're going to work a lot with these well-structured graphs, and it sort of looks like this is a very restricted special case of directed graphs. But in fact, you can take any directed graph and turn it into a graph that looks like this using a really simple transformation. So it's actually just sort of convenient way of representing a directed graph. So going back to residual flow network, well, we automatically get this property. We don't need to worry about it. So this means that every vertex has either in degree at most 1 if it sits on the left, or out degree at most 1 if it sits on the right. Yes?
So the transformation that you mentioned, is it just by replicating vertices or like, so let's
Splitting every vertex into two, one gets incoming, one gets outgoing, and this edge becomes special. Yeah. Okay. So now we know that every vertex has either in degree at most one or out degree at most one. And going back to the residual flow network, what it means for us is that if you get any collection of S to T paths which don't share any edges, they also cannot share any inner vertices. So this is just sort of useful to keep in mind. And this just comes from this property. So going back again, so this was our goal. We have this residual flow network. We know that there are delta disjoint ST paths. We know delta over polylog such paths. So what I'm going to do next, I'm going to define a problem and called route and cut. So this problem, it essentially says compute approximate max ST flow. The route and cut also more or less equivalent. It says compute approximate max ST flow. It's a little bit more general than what we need here, but we're going to use it in other contexts too. So I'm going to define this problem, and if you can solve it, you can solve this one, but this one gives you a little bit more power. So what is this route and cut problem? So we start with a well-structured graph G, and we're given two sets A and B of its vertices. And we want to connect vertices of A to vertices of B with a lot of paths. And now remember, well-structured graphs, they already have this bipartition of vertices, right? So this has nothing to do with this A and B. So any vertex can be in A and any vertex can be in B. And we're also given a target parameter delta, which means that we want delta disjoint A to B paths. So the outcome, the algorithm needs to compute a collection of paths connecting A to B, and they need to be disjoint, inner vertices, endpoints, everything disjoint. And if it manages to compute close to delta such paths, like delta over polylog n, we are very happy and we're done. If not, we want this algorithm to give us a certificate, a proof that it's impossible to connect them by delta paths. And the certificate is simply a cut, so it should be a cut that separates many vertices of A from many vertices of B, and number of edges sticking out of the cut is small. In other words, if you don't want to go into much detail, this is just solve max A to B flow approximately. This is what it says. Now, if we go back to what we wanted to do here, so I'm just going to take all the vertices on the left that have an edge coming in from S, and I'm going to call them A. So these are all these vertices with a green circle. Then all the vertices on the right that connect to T are going to be B. These are the vertices with a purple circle. And now if I ignore A and B, S and T, then this question is simply compute delta over polylog n disjoint A to B paths. In other words, it's simply an instance of route and cut problem. And in route and cut problem, if we don't manage to compute many of these paths, we may produce a small cut that proves that such paths don't exist. But in our case, this will never happen because we know that there are delta disjoint paths connecting S to T. So we will always get this routing, and that's it. So if we can solve this route and cut problem, which is essentially approximate max flow problem, we're done. But it's a little bit more general. In case we can't solve it, we get a cut. So from now on, I'm going to focus on this problem. And again, this is approximate max flow problem. And now, if you want to solve max flow approximately and fast, there is a really cool framework for doing this, and it's called multiplicative weight update framework. And if you're familiar with multiplicative weight update algorithm from machine learning, this does not look, okay, maybe it does look similar. It doesn't look like the same algorithm. But actually, and it's like super simple algorithm, you'll see. But actually, you can do some work, and hard work, to realize that you can cast this algorithm as a special case of that MW algorithm. So they're sort of equivalent, but this is just very simple, and we do multiply some weights, so we can also call it MW because of this. So before I describe this algorithm, I need to quickly describe LPs. These LPs are standard LPs. We will not solve them, they're too big. We're just going to use them sort of to guide our analysis. So I'm going to denote by P all paths that connect vertices of A to vertices of B. And for each such path, there's going to be LP variable f of P, which you can think of, do we take this path into our solution, or as the flow on this path. This is completely standard flow LP. It just says send as much flow as possible along this path from A to B, and the constraint is that for every edge, the flow on this edge is equals to 1. And now we compute the dual, and it's also completely standard. It's actually the min-cut relaxation. And in the dual, we have a variable L of E for every edge E. I think about it as the length of this edge. And then in words, what does this dual say? It says assign lengths to the edges so that the length of every path connecting a vertex of A to a vertex B is at least 1. And subject to this, minimize the total length of all the edges. So this is the dual. Now let me show you the algorithm. It's really simple. So at the beginning of the algorithm, I assign to every edge a tiny, tiny length. It's going to be 1 over this capital N, and this capital N, it should be just sufficiently large, and this number is good enough. And then we do iterations. And the iterations are done as long as there is a path connecting A to B whose length is less than 1. In every iteration, I simply take one such path, send one flow unit on this path, and double the length of every edge on this path. That's it. That's the whole algorithm. Now what happens? Why does it work so well? Well, in every iteration, our flow grows by 1, right? I send one flow unit. The dual solution is the total length of all the edges. It grows by at most 1. Why? Because I take a path whose length is at most 1, and I double the length of its edges. In the end, I get a feasible dual solution because when I stop, there are no short paths connecting A to B. And the flow that I get, its value is at least as large as the value of this dual solution, so I get close to optimal flow, which is perfect. In our case, it's omega of delta, but because we know that there is flow of area delta, but if there is no such flow, you can actually use these L of E values to compute a small cut as needed. Also, you can show that every edge participates in at most log n paths, or carries at most log n flow units. And it's pretty simple because every time that I'm using an edge, I'm doubling its length. The moment it reaches 1, I can't use it anymore because I only take paths of length at most 1. So this is great. We get almost optimal flow, but it causes logarithmic congestion. What I wanted is a collection of disjoint paths, even if it's not so large, even if it's smaller by polylog n factor, it has to be disjoint. So it turns out once you get to this polylog n conjugation, it's pretty easy from here to recover this collection of disjoint paths. I just don't have time to go into it, but you can do it really fast, and it's like completely standard stuff. So it just all boils down to implementing this algorithm so it's fast. And what does this algorithm do, right? The only non-trivial thing is that in every iteration, you want to compute a path connecting a vertex of A to a vertex of B, which is short, and you want to do it fast. And so the algorithm that does it, I'm going to call it the oracle. So the oracle is simply the algorithm that in every iteration it will give us such a path, or it will say, no, such a path does not exist. And the changes that happen is that edges are sometimes doubled. So there is good news and there is bad news. So the good news is that there is this really extensively studied problem called incremental SSSP. And this oracle simply reduces to this problem. And if we had good algorithms for this problem, this would be it. Single social space, sorry, I should have said. Yeah, single social space. We'll talk about it in more detail. The bad news is that this problem is for directed graphs. In undirected graphs, we do have good algorithms for this problem. In directed graphs, no. So what's the main idea of our soda paper? So the main idea is to notice that we can tweak this multiplicative weight update algorithm just a little bit. And what we get as a result is a special case of this decremental single circuitous path, which seems easier. And then what we do, we just take existing algorithm for this decremental SSSP in directed graphs, and we tweak it so that in our special case that we get, it's faster. That's all there is. And actually, I'm going to tell you immediately what is the small tweak of this multiplicative weight update framework. So currently, the algorithm says you are allowed to stop if there is no path connecting A to B that is short. We say, no, it's okay to stop the algorithm earlier. If at any time you realize that the largest number of disjoint and short A to B paths becomes small, you can stop. And small here is less than delta over log squared n, and short, it's even not 1, it's like 1/8. So even if you stop at this point, you're still fine and the whole analysis goes through. Of course, you may wonder, well, it looks very difficult to figure out when this happens. But as we'll see, it will not be very difficult. And actually, it is this little tweak that makes the whole difference. Okay, so from now on, we just focus on designing this oracle. So again, to summarize, we start with a well-structured graph. And the edge lengths are 1 at the beginning. In fact, they're not 1 at the beginning, they're 1 over this capital N. But I'm just going to scale them by n because I want them to be integral. And then we do iterations. In every iteration, I want to compute an A to B path whose length is at most n, and then double every edge on this path. And I'm allowed to terminate this algorithm early if I figure out somehow that largest number of disjoint A to B paths that remain is at most delta over log squared n, and short is n over 8. Now, what I'm going to do, I'm just going to add back the source that connects to everybody in A and destination to which everybody in B connects. And this is just so that I can talk about ST paths instead of A to B paths. It's just more convenient. So even more in a nutshell, what does the oracle want? So we have a graph. This graph undergoes increases in edge lengths. And in every iteration, it just needs to give us a short ST path. And it's allowed to terminate early if some condition holds. And you may say, well, why is it even a problem, right? We all know that there are algorithms to compute a short XY path in a graph, right? Efficient algorithms. But in fact, if you compute this path from scratch, it takes off m time, and it's necessary. And the number of iterations that we're going to have is delta, which can be as large as n. So n times m is running time that we cannot tolerate. So what is the hope? The hope is that we don't need to compute it from scratch, because it's not like every time we have a new graph, right? We have the same old graph that changed a little bit. So we hope we can maintain some data structures that will allow us to do this faster. So what we want is that the total running time of the algorithm should be short, and the total running time consists of 2 parts. First is the time that is required to maintain the data structures, and this is called total update time. And second, whenever the algorithm returns an ST path, I think of it as if it responds to a query. I ask it, give me ST path, it gives me an ST path. And time to respond to a query, it's called query time. So what I want is all of this, the total update time, and the total time to respond to all queries, it should be short. Okay, now what is this decremental single shortest path problem? It's very, very similar, but now the graph undergoes edge deletions, and now edge length increases. And also it's more general, so you can ask queries between S and any other vertex. It doesn't have to be T, and then it needs to return shortest or approximately shortest path. And the number of these queries can be anything. And lastly, usually we require that the time that it takes to respond to a single query is proportional to the number of edges on the path that it returns. So we have a little problem here. Our algorithm doubles edge lengths, and this one only works with edge deletions. But it turns out you can do a really simple transformation so that you can implement edge length increases by edge deletions. And let me quickly show you how. It's very simple. And again, all of this stuff is like really well known. So the way we do it, for every edge in our graph, I'm going to create log n copies. And these are copies of lengths 1, 2, 4, powers of 2, all the way to n. And now what happens is when the length of this edge is doubled, I simply delete its cheapest copy, and that's it. And in this way, even though we undergo edge length increases, we can pretend as if we undergo edge deletions, and so we can use the decremental single source shortest path. Okay, let me now tell you what is known about this decremental single source shortest path. And again, I want to emphasize that for undirected graphs, the problem is like very close to being solved. There are really good algorithms. But for directed graphs, this is not the case. And also here, I will only talk about adaptive adversary because this is what we need. If you don't know what it is, it doesn't matter. It's just for people who know what it is. I just want to highlight that I will not be mentioning the other kind. Okay, so what is known? So first of all, if your graph is a DAG, directed acyclic graph, then there are reasonably good algorithms. You can get 1 plus epsilon approximation in total update time roughly n squared, which is okay. Not linear, but fine. But for general graphs, this is the best current total update time. And if we just take it and plug it into our algorithm, we are not going to get anything. We're not going to beat Hopper of Karp for any density. Okay, so what we do in our paper, the main insight is to notice that we don't need to solve the whole problem. We only need to solve a special case that seems to have a bunch of useful properties. And then there is a hope that we can tweak the existing algorithm so that for this special case it works better. So let me now list you some of these properties. So first of all queries are between a fixed pair of vertices S and T, and we know how many there are. There are delta. And second, and this is like surprisingly, I think the one property that really gives us the edge, is that we only need to respond to queries as long as there is a large number of disjoint and shared ST paths. Also, edge deletions, they're sort of controlled. Edges are only deleted if they appeared on paths that the algorithm returned. And the last one, usually in these single socialist path query problems, you really care about how much time it takes to respond to a single query. For us, if some query takes a lot of time, but other query response times are short, that's completely fine. We just need the total time to be short. So what we do, we simply take this previous algorithm, and we just tweak it so that for this special case, it gives us the fast running time that we need. So let me tell you a little bit about this previous algorithm of Bernstein, Gutenberg, and Sardarak. So the algorithm consists of two main parts. The first part maintains a decomposition of our graph into clusters which are expander-like. So I'm going maybe to call it expander decomposition. And additionally, it supports short path queries inside every cluster. So you give me two vertices inside the cluster, I can return a path connecting them whose length is bounded by the diameter. We'll talk about it in a little bit more detail later. And the last thing, and it's really important, is that if we take our graph and we contract all of these clusters, what we get is a graph that looks almost like a DAG. Why is it helpful? It's helpful because we do have good algorithms for SSSP in DAGs. And we can hope that we can exploit them here in this resulting almost DAG. So now I'm going to tell you a little bit about the second part, which actually does single socialist paths on this almost DAG, and then I'll come back to this expander decomposition. So before I talk about almost DAGs, I need to remind you what's a DAG. So a DAG is a directed acyclic graph, has no cycles. And then we know that we can order the vertices of the DAG from left to right, so that every edge becomes directed from left to right. What's an almost DAG? In an almost DAG, we allow some edges to go from right to left. And then I'm going to define the span of such an edge to be the distance between its endpoints in this ordering. So it's how many vertices sit between the two endpoints plus 1. In this case, it's 3. And intuitively, almost DAG means that the total span of all right to left edges is relatively small. Now, specifically, there is this really cool result of Bernstein, Gutenberg, and Wolff-Nielsen that generalizes their algorithms for DAGs. And it shows that if the total span of all your right to left edges is at most gamma, then the total update time of their single socialist path algorithm becomes n squared plus gamma times n. So it's good not just on DAGs, but also on edges that look almost like DAG. Yes?
So is this for any ordering, any top sort ordering, or?
Yeah. If you have any, it doesn't matter how you order, yeah. As long as the total span of these right to left edges is small, yeah.
So is that invariant across orderings, or that can change?
If what is what?
Is the total span invariant across different sorted orderings, so that can change depending on the ordering?
No, you just need to have to maintain one ordering in which, but this ordering, it has to be consistent, right? If you split a vertex, then the two, because they correspond to clusters, right? If you split a cluster, then the two vertices are split, and then they need to be next to each other. That's the only thing. All you need is just one ordering. Now, if we look at the general single socialist path problem, even if all the queries are just between S and T, then it's possible that the shortest ST paths, or even all shortest ST paths, contain a lot of these right to left edges, maybe all of them. But in our case, we only need to respond to queries as long as there is a lot of short ST paths. And so these right to left edges, they have to be distributed among these short and disjoint ST paths. And so there has to be at least one short ST path that has relatively few of these right to left edges, and their total span on this path is relatively small. And it is this fact that allows us to make this algorithm faster. So this becomes an anytime of this algorithm. And so when this delta is large, we really win. We get much faster algorithm here. So this is all I wanted to say about this part. So this part is just noticing that this algorithm just works better in this case. And now I want to switch to the expanded decomposition part. So for the expanded decomposition part, let's first talk about cuts in directed graphs. So what's a cut? Well, as usually, it's just a partition of vertices into two subsets, x and y. In this case, we'll think of them as ordered, so xy is different from yx. And we have edges going in both directions. Now, we are in this well-structured graph scenario. Remember, we have these red special edges, and every vertex is incident to at most one of them, and then the rest of the edges are regular. So we'll insist that all the edges that go from x to y, all of them have to be special, the red edges. The other direction, we don't care, they can be special or regular. And we say that the cut is phi sparse, and this is standard, if the number of these red edges going from x to y is bounded by phi times the number of vertices on the smaller side. And then we say that the graph is a phi expander if it has no cut of sparsity less than phi. And just like in undirected graphs, if your graph is a phi expander, for every pair of vertices, there is always a path connecting them whose length is roughly 1 over phi, log n over phi. And it's in both directions, so there's going to be a path in this direction and a path in this direction. So now, what we want to do is we want to maintain expander decomposition of our graph. What we're going to do, we'll define a basic subroutine called maintain expander that is responsible for maintaining a single cluster in this decomposition. And then we'll apply this maintain expander to every single cluster in the decomposition. So what is this maintain expander problem? So we start with some well-structured graph, but for us this is going to be just one of the clusters in the decomposition. And this graph undergoes edge deletions. At any time, we may be asked a short path query. So we're given two vertices x and y. In addition to g, we're also given this distance parameter d. So in a short path query, we're given two vertices x and y, and we need to return a path connecting x to y whose length is at most d. And we need to do it in time that's proportional to the number of edges on the path. And obviously, it's possible that such a path does not exist, right? Or maybe, this graph had a small diameter at the beginning, we deleted some edges, and it stopped having a small diameter. So to avoid the situation, we allow our algorithm at any time to produce 1 over d sparse cut. And this is sort of like an evidence that, the diameter is not good anymore. And when it does, we just delete the smaller of the two sides from the graph, like this. And then the algorithm needs to continue with the remaining part. So let me quickly show you how this allows us to maintain this expanded decomposition that we wanted so much. So first, I start with my graph G, and I think of my expanded decomposition as containing a single cluster, and it's G. And I apply this maintain expander problem to G. And then maybe after some time, or maybe immediately, this algorithm produces some sparse cut in this graph, A and B. So now in my expander decomposition, I'm going to replace G with these two clusters, A and B, but I'm going to order them like this, first B and then A. And the reason I'm doing this, it's really important for me that there are few right to left edges, right? And because this cut is sparse, the number of these red edges going across is really small. Now, after this algorithm returns this sparse cut, one of the sides of the cut is deleted from that cluster, so maybe it's A. So the maintain expander problem on G continues with the cluster B, and we start a new maintain expander problem on A. And then maybe after some time, again, we get a sparse cut xy of A. Now we replace A with y and x, again in this order, so the number of right to left edges is small. And at all times, on each one of these clusters, we run this maintain expander problem. Now, remember this maintain expander problem, it comes with this distance parameter d, which is roughly speaking the diameter of our cluster. And it's really important how we choose it. So it's going to be different for different clusters. And we need a total diameter of all the clusters not to be too large. Why? Because at the end we're going to contract these clusters, and then we're going to compute a short ST path in the contracted graph. When we open them back, we don't want them to contribute too much to the length of the ST path. So we want their total diameter to be small. And also, remember, we need a total span of all right to left edges to be small because we needed to make our algorithm on almost DAGs fast. And this number of right to left edges, it depends on the sparsity of these cuts. And the sparsity of the cut is roughly 1 over d, so that again depends on this parameter d. So this d needs to be chosen carefully, and it turns out that this is the right choice. It's sort of similar to what was done previously. It's the number of vertices in the graph divided by delta. But the really important thing to notice here is that it may be really large. It could be like square root n, or I don't know, some polynomial in n. Okay? Okay, so now we go back to our maintain expander problem, and if you don't remember the definition, it's not important. So I'm going to denote by phi 1 over d. At a high level, what does this maintain expander problem do? It's basically given some graph that undergoes edge deletions, and we want to maintain this graph as a phi expander. And the only action that we're allowed to do is cut off sparse cuts from this expander. And then we need to support some short path square. It's not very important. But the bottom line is that this kind of a problem, it just arises all the time, and it has been studied a lot. Much of this in undirected settings. For directed graphs, this previous work gives an algorithm whose running time m over phi squared, which for us is md squared. And typically, when this problem is used, phi is something like 1 over polylog n, and this running time is completely fine. And most of the algorithms also in undirected graphs, this is what they're going to do. But for us, this d, it may be polynomial in n, and this dependence d squared is just too much. This is not working for us. So again, in our soda paper, what we do is, again, we notice that there are some advantages of our setting, and we exploit them to get an algorithm whose running time is md plus n squared, which is enough for us. And I just want to say a few words about how we get this. So this part of the algorithm uses completely standard techniques. But because we're happy with n squared running time, we actually simplify a lot of them significantly. Like some of these techniques, like the cut matching game, we get completely elementary algorithm for it. And again, this md plus n squared running time, so it actually only works for like this restricted setting that we get for a very specific setting of parameters, which is good enough for the soda paper, but is not at all good enough for the n squared time that we wanted to get in the end in the stock paper. So now I just want to say really a few words about what we do in the stock paper. And so in the stock paper, one of the main observations is that if you want to solve this maintain expander problem fast, it's enough that you know how to solve route and cut fast. It's not a trivial reduction, it requires some work, but this is what we show. So in other words, if you get a fast algorithm for route and cut, in the stock paper we notice that you can then get fast algorithm for maintain expander. And in another direction, it's also true. We have seen this already from the soda paper. You just use multiplicative weight update and SSSP almost dance. This observation looks completely useless because what we're saying, well, here are two problems that we want to solve, and if we know how to solve one of them, we can solve the other one, right? So to break out of this chicken and egg problem, what we do is we parameterize both these problems. So if you look at this maintain expander problem, it comes with this distance parameter d. And we say that this instance is R-restricted if this d is bounded by 2 to the power of r squared log n. Some growing function, are not important what it is. If we look at the route and cut problem, well, if we manage to route delta paths from A to B with conjugation at most c, then it's easy to see that most of these paths, they cannot be too long. The length is going to be something like n delta over c. So I think of this n delta over c as my distance parameter, and I'm going to say that this instance is R-restricted if this distance parameter is bounded by, again, the same growing function of r. And then the reductions, we just do them a little bit more carefully. We just say, if you get a fast algorithm for R-restricted route and cut, then you can solve R-restricted maintain expander fast. But in the other direction, you get from R-restricted maintain expander to R+1 restricted route and cut. Now, when r is equal to 1, both of these problems are really easy because this is when this distance parameter is small and you can solve them using all techniques. And then you do induction on r, and simultaneously for these problems, you prove that you can solve them for the whole range of parameters. And there is like one last little thing that I want to mention. So remember this route and cut problem where we wanted to connect vertices of A to vertices of B with disjoint paths. So the final running time that we get, it looks like this. It's roughly n times n minus b. So in case where this b contains almost all the vertices, it's actually really fast. And it's actually maybe even faster than the time that is required to read all the edges. And this may be useful in its own right, but it's actually crucial for us to get our reduction to go through. And basically that's it. Let me summarize. So we get two combinatorial algorithms for bipartite matching problem. Both of them are faster than Hopf-Karp and matrix multiplication if the graph is sufficiently dense. The first one from the Soda paper is deterministic. It gets this running time. And the main idea is just, to notice that with a little tweak of existing techniques, you can reduce the simpler special case of singles or shortest paths. And then again, a little tweak of existing algorithm, you can get faster algorithm for the special case. And Stock paper is randomized algorithm. Running time is close to n squared. The high-level idea is the same, but it's much more technical. And lastly, what are the open problems? Well, obviously, we want now to push all the way to almost linear time algorithms. Another question is whether you can use the same techniques to get algorithms, combinatorial algorithms for max flow, min cost flow, and all of these related problems, which are really important. And last on this one, I find very intriguing is that general matching, still the best, fastest algorithm is m squared n. Can we somehow exploit these techniques to get even a little bit faster than that? Because for this problem, we don't have anything. We don't know how to use continuous techniques, and things were stuck here for a very long time. And that's all. Thank you. Questions?
Oh, Madhur, you can go first.
Okay, so question a little more about the continuous techniques, but so in this multiplicative weight update it's a combinatorial algorithm, but it's a primal dual. It's sort of
Primal dual is only used for analysis, right?
Sorry.
I mean, primal dual is just used for analysis.
Yeah, but I can get this combinatorial algorithm by looking at the LP, thinking of the primal dual, and then do that. So the current whatever convex relaxations are used for this almost linear time max flow. Is there a kind of a combinatorial interpretation of that convex program if I try to look at it in a primal dual way, even if I don't know how to implement it fast?
First of all, I don't know, but people who do know say no.
Okay.
I don't think so.
So this might be the same question. I'm not sure. So maybe the second question is this the same question? But in some sense, what you're doing here, I mean, so this idea of having like a approximate method and using a sequence of approximate methods to get a good method is exactly what's happening in your point methods and in all these continuous methods. So is that like, I mean?
No, but the thing is, like a lot of people are asking this. Like it's not like we're after pure combinatorial algorithms for whatever abstract reasons. And now, for example, I often work on dynamic algorithms. And I know that this, multiplicative weight update, all this stuff, it just fits in so naturally with the algorithms that we have here, when this stuff is just usually not.
I mean, would you be happy if you took the continuous methods and recast the exact same method but understood it directly as an explicit algorithm? Would that
So this would solve part of the problem, right? But the question is, can you still use it in distributed online dynamic? Can it help you with, so for example, bipartite matching in general graphs, right? All this machinery of multiplicative weight update, all that stuff, it just fits completely natural, augmenting paths. This is how I can just imagine using this. But how do I use continuous techniques for that? And actually one of our motivations was, like, we want to get there, right? But to get there, you do need to get better combinatorial algorithms for bipartite matching. So this will probably solve part of the problem, but not all, right? So you're asking about interpretability,
yeah,
which is a good thing, but there is more stuff, right?
Well, I'm asking whether interpretability is, whether your problem is interpretability, or if there's, is there some other sense, I realize it can be like formally defined, but other than, I mean, do you see the main problem in analysis, or in terms of the algorithm itself, there's some defining characteristic of continuous methods that are, that these are, that what you're doing is combinatorial versus, like if I look at mechanic, not in terms of the analysis or the motivation, but in terms of, what are the operations that are actually being performed? Is there a sense in which?
I don't know, but like what I do know is that for some problems we just don't know how to apply those methods, such as general matching. So there must be some difference, I don't know. I mean, maybe also not every combinatorial algorithm will help you with general matching, right?
Other questions?
Quick question. So do you have, for the original multiplicative weight update problem, do you have a sense of whether, so you relax it, solve it, with the 1/8 and so we're able to, for the original version, like is it believed not to be doable that fast or?
The original version, I mean, the main difference is that we stop earlier and there you just need to stop when it gets all the way. No, I mean, there is no negative result, right? The thing is just we gain a lot from the fact that we can stop earlier and that's all. But maybe if you repeat this algorithm a couple of times, you will get all the way, I don't know. Probably you can.
Okay, let's thank Julie again.